Here we go.
Hi, everybody. Today, I'm very glad that we invited Jonathan LaRue as the invited speaker to give us a talk. So Jonathan LaRue is one of my advisor when I was doing internship in Merle. So we had a collaboration in many works, and I'm also a big fan of his work. So I'm just going to introduce him by reading his bio here. So Jonathan LaRue is a senior principal research scientist and the speech and audio senior team leader in Mitsubishi Electronic Research Laboratories in Cambridge, Massachusetts. He completed his bachelor and master degree in mathematics at the École Supérieure in Paris, France. And his PhD in the University of Tokyo and University of Pierre at Marie Curie, and working as a postdoctoral researcher at NTT Communication Science Laboratories from 2009 to 2011. His research interests are in signal processing and machine learning applied to speech and audio. He was contributed to more than 100 peer-reviewed papers and 20 granted patents in this field. He is a founder and chair of the Speech and Audio in the Northeast series of workshops and a senior member of IEEE. Now I'm passing to Jonathan, and let's welcome his talk.
Hey, thanks, Joe, for your introductions. Really happy to be here. Many friends who are listening, many friends and colleagues. I'm sorry I didn't get to see you at ICASP, so we get to chat a little bit today. Yeah, today I'm going to talk about give a broad overview of the work that we've done in the speech and audio team at Merle over the last 5-6 years. So it's mainly focusing on the work we did on trying to separate and or recognize speech by multiple speakers and in one or more languages. So without further ado, first, I mean, obviously this is, I'm going to talk about things that are not all my work, but mostly the work of my collaborators, and there's many of them. This is only an excerpt because it's very hard to everybody to fit on the slides. I'm the main players on the papers that I will be talking about today. So most of the credit goes to them. So I'm going to use this roadmap to kind of guide you guys through the talk. And so our main goal at Merle in the speech and audio team was to try to mimic an auditory system such as that of humans in the way we perceive and understand the world in terms of the acoustic world around us. So you have the world, which is for our purpose like some mixture of audio sources, and you have as a system you have some sensors, which are a bunch of ears, for example, that can capture various versions of this mixed audio. And from these sensors, you're perceiving arguably each of the signals that are inside this mixed audio. And then you can perceive these signals separately from each other. And you can potentially do some task on it, such as recognition. If it's speech, you can recognize some text, happen to be, for example, in French or Italian. It can be some other type of signal. It could be noise, and you could be performing like sound event detection. You could identify what kind of sound it is, or you could be doing location, tracking a source, etc. I'd be mostly focusing today on speech recognition when it comes to these kind of back-end tasks, but other things are possible. And I'm going to use this kind of diagram to guide you through the talk and to tell you where we are. So this is our roadmap, and we're going to first start with the simplest case, which is like you have a mixture of audio sources. You only have one ear, so one microphone, single channel, and you're interested in recovering a single signal. So a typical case for this would be speech enhancement, where you have some noisy signal, which in this case is a boring Wall Street Journal sentence mixed in with sound from John Barker's house.
In a fundamental sense, the equity markets have very little to do with what goes on in the commercial bank.
And you're trying to retrieve either the boring voice or the sound behind it, but here, let's say.
In a fundamental sense, the equity markets have very little to do with what goes on in the commercial.
Right. So how do we do this? And there's been this speech enhancement has been sort of like the first major success of deep learning in speech processing, apart from ASR. So like more in the like processing of signals, this has been like the first thing that really worked very well. And both in deep learning methods and in more conventional methods, like a very often used typical pipeline is to, assuming you have some noisy signal in some noisy waveform, you perform some time frequency, you extract some time frequency representation, for example, using the short time Fourier transform. You get a spectrogram that you feed to a deep network. For example, back in the days, it would have been like an NMF system. And you use this deep network to predict a mask that tries to identify which regions in the spectrogram, which time frequency regions are dominated by speech and which are dominated by noise. So the mask is going to be 1, like let's say if it's a binary mask, it's going to be 1 for regions, speech-dominated regions, and 0 for noise-dominated region. Then you multiply, you only keep those regions that are dominated by speech, you invert your time frequency transform to get back to arguably an estimate of the clean speech in the waveform domain. Typically what we do in this case is the mask is real, so we only actually modify the magnitude part of the spectrum, not the phase, and we'll talk about that a little bit later. So what we did at Merle on that topic was to explore both the deep network architectures and the kind of objective function that you need to train it. So you could train a network based on some error between the reconstructed speech, either in the waveform domain or in the time frequency domain, and the ground truth speech that you want. So you typically get a data set that mixing some noise with some speech, where you know the speech, the clean speech, and you can build that objective function like that. And the objective function involves the mask. So there's a bunch of objective functions. Here are just a few. Assume you have some mixture Y of speech S and noise N. So here on the top right, you have like the view of a single time frequency bin. You assume that the speech S is in this direction, noise is in that direction, and oops, sorry, the mixture Y is the sum of both. You can use like the so-called mask approximation loss function, where you basically try to minimize the distance between your estimated mask and some ideal mask. This is fine, but not as good as trying to directly minimize the distance between the reconstructed magnitude that you obtain when multiplying the mask with your mixture magnitude and the true magnitude, for example. But as it turns out, because we're only using, in most cases, the noisy phase, and you see that there's this angle theta between the clean speech and the noisy speech, you can never, even if you were to actually get the true clean magnitude, it would not be the best thing, because it would be, it could be further away from the true speech than the orthogonal projection of the speech on the noisy mixture. So what Hakan Edron and us proposed was to use this phase-sensitive spectrum approximation, which takes into account the angle between the speech and the noisy mixture. So this objective function is still in use today in many methods that use the time frequency domain. So this was one of the contributions we did. Another one was to look at architectures, and one of the architectures that we found what worked really, really well for these kind of models was recurrent neural networks based on bidirectional LSTMs. So here's a typical architecture. You would have some input STFT frames, for example, or input feature frames that you feed to LSTM layers, both in forward and backward directions. You do have multiple layers of this. And then at the end, at each time t and each frequency f, you estimate one mask value. So the output of a network is one mask value for each time frequency bin. And basically the network learns to have a good value there that leads to a good reconstruction of speech. And it worked very well. So in the example I played earlier, this is what we got for the BSTM with PSA.
In a fundamental sense, the equity markets have very little to do with what goes on in the commercial banks.
So you can hear some artifacts, but it's very good. Okay, so that was the our first introduction to deep learning for speech processing. And then we looked at, this was in single channel, we looked at the multi-channel extension of this, and I won't talk too much about this, but just briefly what we did was to apply single channel enhancement to each of the channels in the multi-channel signal, multi-channel mixture, get masks for speech and the noise. And using these masks, we can identify the bins, the time frequency bins that are dominated by speech and those by noise, and it greatly helps. Computing the speech and noise statistics, the power spectral density matrices that are needed to compute the NVDR beamformer. So we can use this to improve, to get a good beamformer. And we showed that it helped for ASR. Then one of the topic that I'm going to spend a good chunk of time on is speech separation. So you have like still a single channel, but you're interested in retrieving multiple signals potentially of the same type. And in this case, it's speech. Sorry if you have some background noise. My daughter seems to be not happy. So we were interested in single channel speech separation. And why was that? That's because this was supposed kind of to be the holy grail of the cocktail party problem, where for 70 years, people have been trying to separate unknown speakers using a single microphone. Like humans are pretty good at just narrowing down on just one speaker in a crowded room. And this was thought to be difficult for computers. And why is it difficult? Well, when you consider separating speech from noise, the speech and the noise are very different types of signals. So you can imagine that you could train a network to classify between the two, for example. When it's speech versus speech, there have been methods that were able to separate two speakers, but they were relying on the speakers being known. So you assume you had some data from speaker A and speaker B, and you train a system just to separate these two speakers. But separating unknown speakers was considered a challenge, and so we were interested in solving that. So the goal is you have these three speakers sticking together, and you want to retrieve their signals. All right, so again, looking at a typical pipeline, we wanted to train a network to estimate a mask that would be able to separate these speakers. So in speech enhancement, we identify speech versus noise regions, and speech separation, we're like, well, we want to identify speech versus speech regions. So how do you tell the network to do this? And our proposed method was to ask a different question. So instead of asking the network to tell us if a particular time frequency bin is dominated by speech or noise, or in this case by speech or speech, which wouldn't really, which we thought didn't really make sense, we asked a network to output high dimensional embeddings for each time and frequency bin. So the output of vector in a d-dimensional vector space, like in our case, typically 20. And we asked the network to create these vectors such that bins that belong to the same source, bins that belong to the same source, I'm not sure where I jumped, okay, belong to the same source, so pairs of bins that belong to the same source have similar vectors, and pairs of bins that belong to two different sources that are dominated by two different sources are different. So it doesn't matter what the source is, it just matters that things belong together or not. And so we train the network to do this, and then once we've done that, we can use like k-means clustering to get together all the vectors that look alike. And then we get a mask from that. The only difference with a typical pipeline is that you replace the output of the network, which used to be a single number for the time frequency mask at time t and frequency f, by a vector embedding. So now you have an embedding vector instead, and you're going to do clustering of that. How do we do this? Well, how do we train such a network? Well, we vectorize the spectrogram. So we have time by frequency. We just align all the time and frequency bins in a giant vector. And we have our one-hot labels, which are the ground truth, which are for each time frequency bin I, which source is dominated. So if we have two sources, for example, we're going to put a 1 in column number 2 if source number 2 is dominating at that bin, and 1 if it's source number 1. And so the problem with that is that the ordering of resources here still matters. So we don't want to use that as our ground truth signal. What we use is the affinity matrix, which is this vector times its transpose, which only looks at pairs of bins and has a 1 if the bins are in the same, have 1 in the same column. So then it doesn't matter. The ordering of a column no longer matters anymore. And we now train a network to output for each time frequency bin I, a d-dimensional vector, such that when we multiply that vector with the with another vector, we just look at the cross product with of pairs of vectors, we get an estimated affinity matrix that looks like the original affinity matrix. So we want these vector to be similar if the sources in the ground truth tells us that the bins are dominated by the same source. And we don't care what that source is. And we do this by minimizing the distance between these two matrices. And these are giant matrices, so we never want to compute them because it's time frequency by time frequency, which is humongous. We don't want to compute this distance, but thankfully, the trace trick allows us to rewrite that in terms of terms that are much, much smaller. Instead of being TF by TF, these terms are like TF by D at most. All right. So this was the first thing we did, and it turned out that it worked very well. We then tried to get fancier and replace the original objective function, this classic objective function, classic deep clustering objective, by other versions. I won't go into details, but it turns out that we found one that worked slightly better, which is related to the k-means objective. And we thought it made kind of sense because at test time, we're actually using k-means to cluster the V matrix, the V matrix bow. So this objective is basically a k-means objective, but if you don't constrain anything, the network can just decide to output 0 for everybody, and then the k-means objective would be great because everybody would cluster into one cluster. And so instead of doing that, we whitened this matrix to avoid this kind of ill-posed solutions. And it turns out this works best. So here's an output of an example of something we did at a press release event in Tokyo, which was a lot of fun. You're gonna see, so we're gonna talk together at the same time, and then I'll play what the computer heard and what was separated.
Changes for the better is Mitsubishi Electric's corporate statement.
First, here's what was heard.
Changes for the better is Mitsubishi Electric's corporate statement. 鎌倉花火大会が7月19日に開催予定。Changes for the better is Mitsubishi Electric's corporate statement.
So that worked pretty well. And
hey, Jonathan, quick question.
Yeah. Yes.
Was that real time? Meaning, was the separation done while you guys were staring at that screen?
Yeah. What you saw was the actual time of compute, what it took to compute on my laptop.
Excellent.
Yeah. Thanks. This is like, turns out like, why would you want to use this? I mean, it turns out that you could maybe use this to, like you're maybe thinking that it's, most of the time people don't talk over each other in an obnoxious way, right? But it turns out that there's some situation where it could be useful and it may be relevant right now in this period with the election coming up.
Wrong.
National debt of the United States.
You're wrong.
You're wrong. It's playing a really
wrong.
That is absolutely
wrong.
Proved over and over again.
Wrong.
We actually had.
So I mean, what can you do with that? Let's see.
National debt of the United States. It's playing a really. That is absolutely proved over and over again. We actually had.
All right, so we didn't train on these voices in particular, but it turned out that it worked pretty well. Oops, all right, enough. So I mentioned earlier that we thought originally when we did this deep clustering work that trying to ask the network to really just separate two speakers in that just compute mass that would separate the two speakers shouldn't work. I mean, we thought it was like, it was ill-posed, and so it wasn't likely to work. And we actually we used this as our kind of Stroman baseline in the original deep clustering paper, where and we said, look, it doesn't work. But I guess we didn't put enough hard work in it because it turns out that other groups, especially at Microsoft, were able to make it work really well. So I'm going to explain what this is. And basically, so if you ask the network to output a mass value at each time frequency bin, depending on which speaker dominates, you just basically ask the network, just give me estimates, like 2 different estimates. And then I'm going to compare them to the 2 speakers. But I don't know if the estimate number 1 corresponds to speaker 1 or speaker 2. And same thing for estimate number 2. So I'm going to compare the pair estimate 1, estimate 2 to speaker 1, speaker 2, and to speaker 2, speaker 1, and see which permutation is the closest. So we just say, okay, try something and we'll give you benefit of a doubt and just look at the loss that is the smallest. And so it turns out that if you backpropagate through the smallest loss, you can actually train these networks, and it works pretty well. So this is the permutation variant training, PIT, I'm assuming many of you are familiar with. And so what we noticed though is that deep clustering still helps. And if you combine it with this mask inference using PIT kind of loss functions, you do get better results. And so how does this work? So let's assume you have basically the mask inference networks and deep clustering networks are very similar, as they only differ in the output. So in our case, we would have a stack of BLSTM layers, and for deep clustering, we would have a linear layer that computes the embeddings for each time frequency bin, and then we have a loss function, deep clustering loss function based on these embeddings. And for the mask inference, we would have just another linear network that just outputs one number for each time frequency bin, and a mask inference loss function on that. It turns out that if you use both loss functions in a multitask objective, that trains much better than just using the mask inference. The advantage of the mask inference over DC is that deep clustering, because you're doing k-means, it's a little bit cumbersome to train through k-means to minimize for best approximation, for best reconstruction. So it's much easier to do this in the mask inference network. Nonetheless, the deep clustering objective acts as a sort of regularizer that helps train the BLSTM stack. So we really noticed that this is what worked best for us. Now, everything we've done so far has been focusing on estimating a real mass that only modifies the magnitude. And we've only been using the mixture phase or the noisy phase. And why is that? This is a problem. So if you have a speech, I'm looking at in the complex plane in one time frequency bin. So you have like the complex spectrogram of one time frequency bin for the clean speech here. So you have the noise, and then the mixture is here. So you see that the mixture is pointing in a completely different direction from the clean speech. If you look at the closest point to the clean speech with mixture phase, it turns out that it's opposite to the mixture. So this is actually the phase sensitive filter that I mentioned. I mentioned with this phase sensitive approximation, but this is what corresponds to what you would be using here. And most of the time we say, well, that's maybe a bit too crazy. So we're going to truncate this to be this approximation to be between 0 silence and the original mixture. So we want the mass to be between 0 and 1. So your estimate to be between 0 and the mixture. So basically in this case, your best guess is silence, which is a bit sad. But if you were to use if you were able to guess the real magnitude of S, using it would actually be worse if you were using the noisy phase, because you would be going further in the wrong direction. You would be landing here. So this is the ideal amplitude mask estimate. And so this is using the noisy or the mixture phase is a kind of a reason why you have to be conservative in your mask estimate. And people typically use masks that are between 0 and 1, because it's very risky to estimate masks that are better at estimating magnitude because they can lead you in wrong directions. So what can you do with this, about this? So this turns out that if you had a very good magnitude, maybe you could reconstruct the phase that corresponds to it instead of just using the noisy phase. And there are many algorithms for this. A very famous one is the iterative STFT by Griffin and Lim, where you have your given desired magnitude A, like for the estimated clean speech magnitude, you have some estimate of the fifth phase, and you do an inverse STFT to get a waveform, you get a new STFT, you land in a different plot because the phase and the magnitude don't match each other. So there's going to be cancellations, and your STFT is going to be different. So you say, no, I only keep the phase of that. I replace it with my intended estimated clean magnitude, and I start again. And if you do that, at some point you're going to converge to a point where the phase kind of matches more the magnitude. in the case of speech separation, we actually have more information because we have two sources. We have two magnitude estimates for each of the sources, and we know that the sources must sum to the mixture. And this constraint is of huge help because it really guides the phase that can be used for each of the estimates. There's an algorithm that takes this into account. It's called multiple input spectrogram inversion, and basically it does Griffin-Lim, but there's an intermediate step where instead of just using the inverse STFT, it looks at the error between the mixture and the sum of reconstructed signals and distributes that error. It redistributes the error into the two sources before doing the STFT again. So we thought maybe we could use this as a deterministic network at the output of our magnitude estimation network. So we have at the bottom a magnitude inference network, mask inference network that estimates a magnitude. And then we have these layers, which are just basically a bunch of inverse STFT, redistribute the, so it's depicted here, inverse STFT, redistribute the error between the sum of sources and the mixture, redo STFT, take the phase, recombine with magnitude, and then do this again. So these are all deterministic steps that you can just code in a deep learning toolkit very efficiently nowadays. And so you can have these layers and you can train these BLSTM and this linear layer all the way through all these deterministic layers based on some objective function, which is the error between the reconstructed waveforms and the true waveform. So we tried that. And so this shows that phase reconstruction helps. So here are a bunch of SISDR results on this Wall Street Journal 2mix dataset that has been used a lot. And this Chimera++ network is the mask inference plus deep clustering that I mentioned, get 11.2 dB. If you use this MISI algorithm to reconstruct phase, just as post-processing, you get 0.3 dB improvement. If you train through these 5 layers of deterministic MISI, you get a whole 1 dB improvement to 12.6. And actually all these STFT and ISTFT layers, they're just, like 1D deconvolution layers, so you can actually train them. And we tried that and it gets a small boost. What's interesting here is that the one thing that we didn't try to train was the first initial STFT. So if you look in here, the log magnitude here of the STFT, we didn't try training this. And it turns out that partly we lost a lot here because most of the methods that outperform Chimera networks nowadays are based on directly estimating a transform from the time domain, like TASNet, for example. And one of the reasons why they work so well also is that they're able to exploit a much shorter window. So they kind of trade, they don't use the phase they don't have to use the magnitude versus phase because their phase is kind of encoded in these very short windows by looking at very small shifts on these windows. All right. So this was only like a band-aid on the phase, but could we actually directly estimate a better phase from the get-go? We tried that, and in our work on Facebook and Friends, the idea was to try to train a network to estimate a phase, but phase is a bit annoying because there's wrapping issues and like you could have discontinuities around pi minus pi. So having a good representation of phase is not easy. And what we proposed was to represent phase as using discrete representation. So let's assume we're trying to estimate the phase difference between the mixture and the clean speech. And we asked the network to give us softmax probabilities on a set of discrete phase values. Sorry. So let's say in this case, we have 8 phase values that we consider, and the network is going to give us its impression of where the phase should land. And so it's these circles, the area of each of these circles shows kind of the softmax probability that was attributed by the network. And then we do a convex combination in the complex plane to get this point, this gray point, and we project it to get the phase. That kind of sort of a convex approximation, weighted combination of all these things to get a phase. So this is the Facebook idea. We can use kind of a similar idea for the magnitude as well. And as I mentioned, so far people were mostly focused on estimating masks that were landing in the 0-1 interval. But we considered expanding this because we thought there, as I mentioned, like if you get a better phase, then it becomes worth it to get closer to the real magnitude, which means that you have to consider masks that go beyond 1 to retrieve the true clean speech magnitude from a mixture magnitude where there was some cancellation with the noise. So we considered a convex softmax between the values 0, 1, and 2. 0 being like speech is inactive, 1 is this source dominates, and 2 is like it's everything that's after 2, actually, of course. This bump is from over the tail, but it's like there was some phase cancellation, basically. And so if we combine these two, we can get a good complex estimate. Why do we care? I mean, why is it important to, I mean, how much can we get from getting a better phase? So this graph shows oracle performance of many masks, like ideal amplitude, ideal binary mask, et cetera, and using on the left the noisy phase, on the right the true phase, and in between some sort of more and more better and better quality version of a phase by using these Facebook representations with more and more codebook numbers, codebook elements. And turns out that if you look at the ideal amplitude mask, which is the one that I mentioned could be very risky if you don't do anything with the phase, well, it's in here, it's actually towards the bottom of all the oracle masks. But as soon as you start using slightly better phase, it really gets much, much better. And if you truncate it to 1, as was typically done before, it's still very good, but you're leaving in a lot of potential gains just by going up to 1.5 or 2. So that's why we decided to go to 2. Okay, so if you can combine these, yes?
Jonathan, there are a couple of questions in the Q&A.
Yeah.
Chenglin Chu asks, the MISI phase reconstruction will not work in the condition where the mixture is corrupted by noise and reverberation. This is something Maciejewski has also been looking at. And it says, because it assumes that the separated signals are summed to be equal to the mixture. If you take a look, you want to answer it now or do it later?
I mean, I can take a stab now.
Go ahead.
I think it's very true that this is a bit brittle. And if you don't take reverberation in particular is going to be difficult. Like noise, you could imagine that you can treat it as another source. I think reverberation may be tricky. That being said, I haven't looked at it myself, but I'm assuming that there must be ways to put some uncertainty on that, make that constraint slightly less strict, so that like it doesn't have to be exactly equal. But I think nonetheless, the MISI will help because it gives sort of a broad direction. So it's much better than just reconstructing the phase in a vacuum. Because if you don't have any indication of where you should point, there actually are infinitely many solutions. But in the MISI idea is that you just latch on the mixture phase as a sort of beacon of where you should go.
Cool.
So I think it would help to some extent, but yeah, it's likely that it would hurt.
So yeah. Chenglin, does that answer your question? I've unmuted a mic if you want to add anything.
Yes. Hi, Jonathan. I'm Chenglin. Nice to meet you. Actually, if it only has noise, we can use noise as another object, another output. Then we estimate this noise. Then we can divide by the estimation noise. Mm-hmm. Then it works. Yeah, for the reverberation, I think the vibration, because we can assume it as a direct sum and the vibrating part. So mm-hmm. I'm not sure if we overlook the vibration part, does it works well, or we need to.
Yeah, I think it's going to be tricky. One potential approach would be to maybe identify regions where bins where the direct path is maybe stronger, and then use this kind of only use this constraint on the bins where you have more confidence about that the relation holds. And for other bins, maybe you can just use normal Griffin and Lim. I mean, maybe something like that could help. It was just, you know, out of the top of my head.
Okay, so what do you think if we use a vocoder to reconstruct the signal?
I mean, that's another possibility, but then it starts maybe being tricky to train through that. I think maybe there are methods that try to use like I don't know, speech synthesis to do to some extent reconstruct the signal, but yeah, I think it's then it becomes really tricky to train through.
Yes.
Right.
Okay.
Yeah, Jonathan, there's another question which is actually intriguing, and I don't know if you want to take it now, maybe later. Rama Chalappa asks, the source separation idea, can we use that to sort of separate adversarial attack noises from the original speech? So that's an interesting thought. I'll leave it there on the table to answer now or later.
Yeah, I don't have a good answer to that actually. I don't know. I mean, I would have maybe to get a little bit more details on the kind of attack. I mean, typically, I mean, I know that some attacks, like you can actually, if you apply some speech enhancement to many of these attacks, they just die. Like the enhancement algorithm is able to, because these attacks typically use like very, very fine structure. Yeah. If you pass it through like pretty much any denoising algorithm, is just going to mess up with that structure, and then it will no longer work. I'm not sure if we can really train a network to specifically deal with these attacks, but my guess is that like I would need to look at the attack because many of these attacks are very brittle. So yeah.
All right. Okay. It's worth discussing at some point later. Mm-hmm. Thanks. Yeah.
So we can combine these methods into like estimate the magnitude and the phase separately and to get an estimate of a complex estimate of a spectrum, or we actually looked into this yet another discrete representation that directly estimates like complex numbers in the complex planes that you can use a convex sum on to compute your mask. We call this COMBOK. And we trained these networks and we found out that actually it helps, it kind of, you can get the performance that you would have gotten if you use these MISI iterations. Like on this graph, you see the number of phase reconstruction iterations that we do. On the blue one is if you just reconstruct the phase. Just reconstruct the magnitude and use the noisy phase and then some phase reconstructions. And you see that reconstructing phase helps. But if you use these better phase estimates, you can actually start pretty much at where you land after phase reconstruction. So it helps in terms that at test time you don't need to do any phase reconstruction. And all these methods at the end land to pretty much the same number. Okay, I need to probably speed up a little bit. All of these experiments had been done, and many people, like most people, actually focused on this data set that we had put out, which was 8 kilohertz clean speech anechoic mixtures, and performance is really starting to saturate. Like we're getting crazy numbers. Like I've seen like 22, 24 dB separations, which starts to be kind of unreal. But so we thought like now we maybe need to move to more realistic mixtures, and so we released this WAM dataset, the WSJ0 hipster ambient mixtures dataset, which is basically mixtures of the Wall Street Journal clean speech with some background noise that was recorded with the Whisper AI startup in like the San Francisco area, in like bars and cafes and restaurants. And we extended it to include reverberant conditions as well. And so you can get it at this link. This is typically how it sounds.
Some foreign firms won't consider joint ventures without cast-ion estimates will be protected from changes in the...
So a bit more challenging than the original WJ02 mix, and it's also 16 kilohertz. So that is also more realistic in that regard. There are several conditions. So the clean one corresponds to the original WJ02 mix. The noisy is what we call WAM, and then in WAMR you have like the reverberant no noise and reverberant noisy conditions. And we found that in this, we built some baselines, and we found that what worked best for us if you want to, for example, separate two speakers in a noisy and reverberant environment, was to first denoise to get rid of the of a noise only, keep the reverberant two speaker mixtures, and then separate the reverberant mixtures into two reverberant separated speeches, and then de-reverberate to get the separated clean speech. Kind of makes sense because these two speakers are in two different locations, so their reverberation is also different. The characteristics are different, so it would make sense that you would want to de-reverberate separately. But still, this is very fresh. It's from last year, so actually from this ICAST. So there's a lot of work coming out from other groups as well on this data set. And so we found that getting rid of reverb is harder than getting rid of the noise. Typically, the performance is a bit worse. And that if you cascade all these networks and then you fine tune at the end, so you backpropagate the error all the way through all the networks, you get a little bit of improvement as well. All right, so far I've been talking about speech separation. I just want to briefly mention something that is not speech and more like the separation of general sounds. We're interested in this topic because like you could use it, for example, for anomaly detection in machine environments, for example, and it's typically more difficult to create good realistic data on like non-speech applications. Like it's more difficult to record natural sounds in isolation. For example, like if you record a machine, some of its parts you would not be able to hear the sound of each part separately because they need each other to work. So we were interested in this, in what we call this weakly supervised source separation approach, where you have a mixture and you're trying to train a separator that separates depending on the type of sounds and the sound classes within the mixture. Like for example, you have a siren, a dog, car horn, singing person, and you only have what sounds are in the mixture at training time. At test time, you don't have anything. At training time, you only know, well, in this example, there's a siren, a dog, a car horn, etc. Or not. So you only have that information. And so you either have that information at the clip level, so in these 10 seconds, is there or not this particular type of sound, or at the frame level, so at this particular time instant, what is active or what is not active. How can you train a separator to do the separation with only that information? So how do you use these labels? Well, it turns out that you can train a classifier on the mixture, like a sound event classifier, to retrieve these labels, either the frame ones or the clip ones. And then you use that classifier as a critique for the separator. So you ask the separator to separate such that when you feed that signal to the classifier, it only finds the signal for that class and nothing else. And it turns out you can make that work. And here are some results. So on these 5 types of sounds, like the blue is the SDR of the input. In green is if you have the actual ground truth signal to train your model. So this is like typical supervised separation. And in orange is if you have the label at the clip level. And in red, if you have a frame level, so much fine grained activity. And it turns out that, of course, you lose a little bit compared to the strongly supervised case, but still you're able to separate somewhat. Here's an example. All right, here's some outputs. Number one. All right, you get the picture. So, so it works to some extent, and we're interested in this direction. We also did some multi-channel extension to deep clustering, where we use multiple microphones in a reverberant environment, and we wanted to do this in a way that did not depend on the microphone array geometry or the number of microphones. Just going to briefly mention how we did this. This was the best student paper award at ICAST 2 years ago. Basically, we use deep clustering we identify a reference microphone, and then we look at pairs of like speaker reference and each of the other microphone, or the pairs. And we use a deep clustering single channel kind of deep clustering, well, 2-channel deep clustering, I would say, network that looks at the magnitude of the reference microphone and the phase difference between the 2 microphones. We get embedding vectors for each of these pairs. We just concatenate them and then we separate with k-means so that we can aggregate the information across microphone pairs. And this works pretty well. And I can play one example. Here's the mixture.
Yields range from 4.8% off 5.2 points at 1,789.5.
And here we're trying to recover the speech with reverb. You're not trying to de-reverberate. So with one microphone, you get this.
The 100 share index was off 5 points at 1,789.5.
So some artifacts. With 4 microphones, you get this.
The 100 share index was off 5.2 points at 1,789.5.
So much less artifact. All right, now I'm going to switch to the second part of the talk, and I'm hopefully going to get through it. Our second biggest arc in the speech and audio team at Merle was to work towards a multilingual, multi-speaker end-to-end speech recognition engine. And we wanted to leverage the end-to-end direct optimization idea to kind of get a single system that we'll be able to listen to multiple people in multiple languages and transcribe what they're saying without needing any expert knowledge. And it's something that you can just train based on their speech and transcriptions. So how do we go on to do this? Well, first, very briefly on end-to-end ASR. So the idea of end-to-end ASR is that you can train a single network that directly maps speech to a sequence of speech waveform to a sequence of letters or words. It's greatly simplify the system architecture, and then it makes it so that if you change your training data, you can actually use the same architecture to do different tasks very easily. And no need for experts to give you pronunciation dictionaries, tokenization tools, etc. And of course, why didn't people think of that earlier? Well, it's not that easy because the speech waveform and the sequence of letters or words live in very different realms. Like the speech waveform, you can convert into a sequence of feature frames that are like typically 100 hertz frequency. So every 10 milliseconds you have a frame, whereas the words, you can only have a dozen or so in the output sequence, and the alignment between the two is not given. So in order to get this alignment, one approach is to use attention. So a major architecture in end-to-end ASR is the so-called attention-based encoder-decoder architecture, where you have an encoder that creates from the input frame sequence some encodings, typically at a slightly downsampled rate. And then the decoder uses an attention mechanism to predict the next character or next word. So the attention mechanism, given the past, decides where to look in the encoding sequence and then what to output. The problem with that is that there's no restriction where to look. So it could actually look back in the past. There's no monotonic constraint. So what we proposed was to pair this with another end-to-end type of network, which is CTC, Connections Temporal Classification, where there is a monotonic alignment constraint. And if you train these two together, you can get actually much better performance. And you can even pair that with a language model. So this has become sort of a workhorse of many end-to-end ASR systems, and it's still used today. For example, you can pair Transformer with CTC, and it performs very well. All right, so this shows that we first got very good results on languages like Chinese and Japanese, which are character-based. So there's, the output sequences are shorter, and we got back then things that rivaled with the state-of-the-art commercial systems. Then what we did from this was to move on to not only recognizing a single language, but multilingual, multiple languages. And single channel, one speaker, and multiple languages. Very simple. You just expand your output character set from, like, if you were recognizing English, you would have the 26 letters of a Latin alphabet. Now you add other alphabets, for example, and you ask your network to, with your decoder, basically to output characters from that extended set. The way you train this is that you feed, for example, a sentence in any language, and you ask the decoder, the network, to output a language ID tag for that language, and then the sequence of characters that corresponds to the speech. You can even train it by concatenating sentences in multiple languages to handle code switching, and and train it in a similar way. So it's just training the training data, changing the training data and the output, and you can get such a system. And we showed that if you compare the language dependent systems in blue, you have 10 blue systems versus 1 red system, which is language independent. In most languages, it greatly helps. All right. Now we moved on to, after that, we moved on to multi-speaker speech recognition. Given our work on speech separation, we were interested in well, can you actually recognize speech from these separated speech signals? So this is what we did first. So we wanted to have a single network again that can recognize multiple people speaking together, first in English only. And the first idea was to actually separate the signals. So you do your camera network to get 2 masks, you output your 2 estimates, and then you just use your CTC attention encoder decoder system, ASR system, separately on each of the 2 estimates to get 2 output sequences, and you can train using permutation invariant loss on the character sequences. In this case, we pre-trained the separator and the ASR system separately, which greatly helps in training. It turns out that we were interested then in looking in an even simpler system where you wouldn't even separate. You would not explicitly separate the sources, but the ASR system itself would be implicitly doing the separation. So next, we don't use any separation engine. We just feed the input mixture directly to the ASR, and we ask it to transcribe not 1 output, but 2 character sequences. How do we do this? We first train a single ASR system on single speaker speech. So forget about the right part for now. Just focus on the left part. We train the left part, which is just a conventional system with, for example, some convolutional layers at the beginning, then a bunch of DLSTM layers and more DLSTM layers. And then we take that system, we take apart a couple of DLSTM layers in the middle, and so we copy this whole architecture, but we perturbate only a couple of DLSTM layers so that they're different in the 2 branches. These guys, the weights for the final layers are shared. The first few layers are also shared. But there's only these layers are what we call speaker differentiating encoders, and their role is to focus on try to extract different parts of the encoder of a mixture, to encode different parts of the mixture. And then we feed all the rest to the same pipeline. And we train this whole pipeline, again, using permutation invariant training, only given the mixture as input and the character sequences as output. So there's no need to have a ground truth separated signals anymore. And this worked about the same as the explicit separation, interestingly. And it's much simpler, so which is why we use it for our subsequent systems. Now we are getting to multi-speaker, multilingual speech recognition. Basically, we just changed the training data, and we were able to it just kind of worked. So you don't have to look at this, but this is just an example to show you that it actually outputs text that doesn't have so many errors. I'm just going to show now a demo of, so we took this system and had another press release in Japan, in Tokyo, last year, where we got to be on all the TV channels at night in the news. That was fun. And what we did is we built a fake airport guidance system. And I'm going to play a demo where I show how that works. I'm going to pause a little bit. All right, so here you have this multilingual airport guidance system. You imagine you're in the departures level of some airport, which maybe is not going to happen for a while. But just remember the good old days, and you ask the system, you want to ask the system to guide you to some business, like a restaurant, shopping, or some services, in the language that you use to query it. So if you query it in Japanese, if you want the answer in Japanese, query in English, you want the answer in English, etc. And you can use, in this system, you could actually use Japanese, Chinese, English, French, German, Italian. Well, the German, Italian, we didn't build the backend, but it would still recognize the words. And so we had a lot of fun creating all these fake udon restaurants, etc. and I'm going to show you how that works. Ramen ga tabetai na. So I want to eat ramen. It shows me where the ramen shop is in Japanese, Rameicho. I need to charge my phone. Again in English. And you can actually do multiple queries. Chuka ryori ga tabetai. I would like to go to the bookstore. Je cherche un restaurant français. And so we have a free output each in the language of the query. And so this is like one speaker with code switching, but you're going to do multiple speakers speaking together at the same time.
I'd like to buy a necklace.
And so the necklace, the jewelry store, and the toy store in Japanese. All right. And people could play with it at the press release. Now we've gone to multi-speaker, multilingual. We thought, well, why not do it multi-channel? So we first did some multi-channel single speaker. This was done by Tsubasa Ochiai in 2017. And this basically the idea is to piggyback a speech enhancement system, multi-channel system where you have some masking network that extracts the mask over noise in the speech to build the NVIDIA beamformer. Then you have feature extraction and your typical speech recognition engine, but all the steps are built such that they're differentiable. So you can backpropagate the error all the way from a transcription to the original, to the first masking network, and optimize everything. And this helps for speech enhancement. Then we looked at this at multi-channel, multi-speaker, multilingual speech recognition. Actually, we did not do the multilingual part, but as you know, it's just a matter of changing the training data. And Xuan-Kai Chang at JHU, student of Shinji, did this at ASIU and got the best paper award for it last year, where it was a multi-channel, multi-speaker end-to-end ASR system. Very similar idea to that of Ochiai, but now we are outputting a mask for the noise and each of the speakers, and we use that for beamforming. And instead of just one ASR system, we have two ASR systems in the back. And turns out that you can, this actually learns to separate. Like if you look at a mixture, even in reverberant condition, to some extent it does separate.
And some
so an hourly operator was promoted to foreman, but maintained on the hour.
Just going to play part of it. Oops.
And some chains, such as Holiday Corporation, Sheraton Corporation. And
so this is in reverberant conditions, slightly reverberant conditions. It turns out reverberation is really causing the most of the issues for this kind of system. In anechoic conditions, it works. It can actually learn to perfectly separate just based on transcriptions, which is interesting. And the last work I want to mention is the follow-up to this work where we, instead of using BLSTMs in all these networks, we use transformers. So we replace the encoder and the decoder of the ASR system by transformer. And then what's interesting in particular here is that we also use transformer in the masking network. And this is the first time to our knowledge that self-attention was used for speech separation. And because this is a much higher frame rate than for ASR, we had to use like a time-restricted self-attention in order to make it work. Because self-attention is very memory and computational, its cost is very high. All right, so we compare now the RNN-based, BLSTM-based, multiple input, multiple output speech system with this transformer counterpart. We see that in anechoic conditions, it was already working almost perfectly, so there's almost no gains. In reverberant conditions, there's a little bit of gain if you don't try to do anything about reverberation. So the transformer by itself cannot really deal with reverberation much more than the BLSTM. And if you use a dereverberation engine, both at training and test time, so you pre-process with like NaraWPE for dereverberation, you get a huge jump in performance in both cases, and a transformer again is a bit better. All right, I think I'm about done. I just want to mention very briefly, this is my last slide, some of the directions we're going. I mean, in recent works, something that's already out, we've done a lot of work on making all this run online or faster. A big part of making the press release demo last year with this guidance system work was to have this vectorized beam search that allowed us to get a 33x speed up on GPU for an attention on LLM system, 12x speed up when also involving CTC, and which solved all our problems when it came to having a real-time demo. And then Nico Moritz has been working a lot on on developing a streaming end-to-end SR engine at Merle. And he's done like a bunch of works at IntoSpeech and ICAST, SIU, and ICAST again. And he was able to get the state-of-the-art performance as of January on online and Libre speech task. Then we're also trying to use less supervision, less paired data. There was a work at the Geninet workshop 2 years ago led by Takaaki Hori on cycle consistency training for end-to-end SR. So you have a bunch of speech, you have speech data, you have a bunch of text data. But they're not paired. How can you use them to improve your performance? And then we also did work on bootstrapping unsupervised separation with Prince Darman at Northwestern University, where for one example was, let's assume you have a simple system that relies on stereo channels and spatial information to give you a crude separation. You can use that to get, and you don't have any ground truth signal, you just have mixtures, stereo mixtures. You use that to kind of build fake ground truth isolated sources that you can then use to train a single channel system. And finally, we are interested in tackling more general and realistic scenes. One example was the work that we did jointly with folks at Google on universal sound separation. And I think I'm done.
Great, thank you, Jonathan.
Thanks, everyone.
Great. So we have time for a little bit of Q&A. Joe, if you would like to come back as well. So Jonathan, let me tee it off with a question that Rama Chalappa again asked in the Q&A box. He notes that most of the methods you talked about are either supervised or semi-supervised scenarios. And he's asking, first of all, you can comment on whether or not you agree with that characterization. And secondly, he's saying, are unsupervised methods of interest? Where do they arise? And by unsupervised, what he means is, if we don't know something about one of the sources that's interfering, maybe we know about the other, can we then separate them? Like, and his toy example is, what if Martians started talking with us, or while we're talking? We don't know what Martian speech sounds like, but could we separate them? Or I can imagine things like, if there's some animal making noises and somebody's talking, can we separate that out? Basically, one source unknown, maybe.
Yeah, I mean, I think, yeah, so we have worked mostly on supervised methods, indeed. I just mentioned briefly this weakly supervised setting, and I just mentioned like that we are very much interested in using less supervision. There was a recent work, not by us, but I mean, that's actually presented next week by Scott Wisdom and colleagues at Google on unsupervised training of speech separation based on mixture of mixtures, which is very interesting, and I encourage you to check. So there is interest in going into these kind of unsupervised methods, definitely. Then there's also the question of, can you train a system to just extract speech and nothing else? Well, I mean, speech enhancement methods are kind of doing that. I guess if you have a training set that has enough variety, you can hope that maybe with novel sounds, it would still be able to cancel them to some extent, especially if it learns to really reconstruct what speech is. So if, like, you could imagine using like autoencoder kind of methods that are only able to reconstruct speech and nothing else. So even if you perturb them with something that you've never heard before, I mean, they can only reconstruct speech, so they could not reconstruct that something else. So maybe this is a direction of interest. Yeah, I would say, I mean, this is definitely a direction of interest and a hot topic, like very fresh topic.
All right, again, let me urge the audience to raise their hand if they like, and I can turn on your microphone and you can ask your questions orally, and we can take it from there. Oh, by the way, Rama points out that Kavalerov is his PhD student in the last reference that you have in the slide. So, all right, anyway. Yeah, so please, audience, we have a couple more minutes for questions. Anything else? I see Haizu, Mari, a lot of distinguished people in the audience. If you have any comments, or Alex, comments from you?
I had a very simple question, which is typically how much training data do you need for these different scenarios?
Yeah. In most of the, like for example, the speech separation, most of the work that we've done was using this WSJ02 mixed data set, which has 30 hours of training data. By no means it means that it's enough. And I mean, it's interesting that us included, almost nobody ever thought of using more data, like creating more mixtures. So you can create as many as you want. And only recently have we started seeing papers where, well, I'm just going to create more mixtures with the same data. And I mean, we did not publish on this, but actually our colleagues in Japan were interested in making this into products. Like they're like, well, if you use 130 hours, it works much better. We knew this, but somehow like we got lazy and never actually got to use that in a paper. But yeah, it does help if you increase the amount of training. And for the ASR system, I mean, the training data is typically could be in the like 1,000 hours range.
Also, I have a speculative question. It really has to do with novel sound sources. So it seems that given the various techniques that you've assembled, would it be possible to adopt a iterative subtractive approach?
Yeah. Yes, and it's possible, and actually people have tried this, and there's especially a lot of work on this at NTT, where they have a system that is attention-based system where they're trying to build a mask that says, I'm going to look at this part, I'm going to separate that part, and then I pass the rest to a second version of the network that kind of deals with the rest and then separates again. And yeah, it's very interesting. They got success in doing that, especially for long recordings where they can track. They pair that with some notion of the speaker ID, so that they can track who is speaking. Even if they become silent, then speak again, they can really keep them in the same stream of speech. So yes, indeed, they're using these kind of iterative methods is a solution, one solution.
Thank you.
Thanks.
So Themos has his hand up. Themos, go ahead and ask your question after.
Yeah. Hi, Jonathan, and all. Thanks for the talk. I'm wondering regarding audiovisual speaker separation. If you are aware of methods coming, for example, from University of Oxford, Andrew Zisselman's group, or Dongyu from Tencent, that also use lip information or other cues, visual cues, and have demonstrated some really amazing results. I was wondering how you compare with the audiovisual, because I haven't seen a fair comparison. Okay.
We at Merrill, we haven't looked at audiovisual separation, so I don't know how we compare. I'm assuming that they perform better because there's so much more information. I'm assuming that Dongyu probably compared to an audio-only system, but yeah, I mean these methods. Earlier, I mean, like in the early days of the audiovisual methods, like, I think there was a bunch of papers that appeared at the same month. Like from Google, from Oxford, and I think Berkeley, and maybe one other group. And in these earlier ones, I was surprised that the vision side did not help more. Like I remember that the Google system only had like 1 dB difference between audio only versus audiovisual. I think now it must, I mean, systems must have improved, and there probably is a much bigger gap because the visual is such a big cue.
Mm-hmm. Okay, thank you.
Yeah, thanks.
Thanks, Themos. Haizu had a question. He typed it in the QA box, but he's also online. So Haizu, go ahead and ask.
Yeah, I just thanks, Sanjeev.
Hey.
Thanks, Jonathan. Yeah, this is Haizu. Wonderful talk. I learned a lot. I have a small question about the technique. Have you tried using the same techniques to separate, for example, voice from different type of sounds, like could be music, for example, whose spectral density distribution is very different from speech.
Yeah, it's a good question. So what we did not do is like, I don't think we ever did speech versus music. We did do singing voice versus accompaniment. Iluo at Columbia had actually the first Chimera network paper was for music, where we separated singing voice from accompaniment. And we also worked on music separation, but we haven't done, that I can remember, speech versus music. Music is challenging, as you hinted. The spectrum of music is much more crowded. So it's having good results in music separation is harder than like in speech separation. But
I see. So just being different is not enough. If it's crowded, it interferes. Okay.
Things overlap, and especially in music, like, you know, instruments play the same notes, or they're in harmonic relationships with each other. So it's you really have to disintricate more like time frequency bins that overlap completely. Whereas for
speech, human voice is like our vocal system is like a more defined, like a more like constraints, like like we are separating two musical instruments between two persons. Like, but music, it could be a lot more others.
I mean, it's speech signals are much sparser. So it turns out that they're easier to separate. Like, and most of the time, people don't speak in harmony with each other. So it's also why it's easier to separate. That being said, I don't think it's impossible to separate people speaking in harmony. Maybe you just need a slightly stronger model of
thank you. Yeah, thank you.
Thanks.
And Mari had a question in the other direction about what if things are too similar. Mari, go ahead, ask the question.
Yeah, I think this is actually a related question, but so your demos, which are very impressive, and I love the talk. I learned a lot. Your impressive demos typically had a male and a female overlapping, and my experience recently is that's an easier problem. And for example, female, anecdotally, in the stuff I was playing around with, is harder. And I'm just curious if you've looked at that, like separated out the performance for different types of combinations, so to understand, you know, where more work is needed.
Yes, that's definitely true. So the reason the video I showed was male female is because for this type of, you know, press release events, we want to just put all our chances on our side.
Obviously, yes.
But so male female is definitely the easiest case. Male, but it's not being said that same gender doesn't work. It works slightly less well, and both ourselves and other groups have published results that compare, you know, same gender versus different gender cases. And it's true that I believe female is the hardest case. I mean, at some point, I think the quality has been getting so good that even being not as good as male female is still pretty good.
Right. No, I appreciate that. Can you say roughly quantitatively what's the difference? What's the degradation?
I can't remember. I think it would be like maybe 2-3 dB difference. We would have to look at the papers. I mean, I don't know if Joe remembers. I think maybe we looked at this at some point, but I would say maybe 2-3 dB difference.
Yeah.
Thanks.
Yeah.
Great. Thanks, Mari. So there's another question. Shrikant Chittapalli, I have enabled your audio. Would you like to ask it orally?
Yeah. Hi, Jonathan. Thanks for the nice talk.
Thanks.
My question was, so most of the separation work and the multi-speaker ASR work, the illustrations at least show that you have 100% overlap between the speakers.
Yeah.
What happens in time, I mean? So what happens if you have like partial overlaps? So generally when you're in a conversation, right? Like at the end of the trailing portion, you have overlap and then the speaker continues. The ASR system, does it predict the silence for the second channel, the second stream?
Hopefully, yes. But you're very right that this is actually kind of a failure case scenario. So originally, we were, like, everybody was persuaded that like 100% overlap was the hardest. It turns out that it's not, and that with less overlap, the systems have trouble like patching things together. So my impression is that very often the systems kind of try to determine what to put in each output by basically who is the loudest. And so if a speaker is louder consistently throughout a scene, then it's going to be easy. But if somebody starts speaking and then and then is the loudest at some point, and then somebody else starts being the loudest, that could confuse the network. And then the separation at every time instant is good, but it may, switch between speakers. And so the recent methods that have shown a lot of improvements, like WaveSplit, for example, are based on tracking some speaker information. Like they're trying to first extract some speaker information, like who are the speakers in this mixture. And then once this is cleared, like they give that speaker anchor to the system. It's like just output that speaker anchor and stick to that, kind of to force the network to follow through. But it's, yeah, in theory, when it works well, that's what it does. It does output silence for the second source. But it's a difficult case, yeah.
Okay, fine. Thanks, Jonathan. And last but not least, John Hershey has a comment, maybe a question too. So John, go ahead.
Yeah, I just wanted to point out, since there was a question about the unsupervised learning, and Jonathan brought up the work that we did recently, I just wanted to say that work has a long history, and it originally came about 5 years ago in the Jelinek workshop in Seattle when we were working on deep clustering, and we were talking about, hey, what can we do in the case where we don't have synthetic data with signal level references. And we thought about this mixtures of mixtures idea, and Jonathan and I came up with ways of doing it with deep clustering. We never really finished the experiments, but it was worked on. And the later work that we came out with at Google owes a lot to that whole trajectory. And it's very similar in spirit because we start with mixtures of mixtures. It just has a different objective function, and there's sort of more like signal approximation way of doing it.
Yeah, we need to put that objective function out. Just maybe somebody else more clever than can actually do something with it.
Yeah. All right. Cool. Thanks, John. Yeah, John. Rama Chalappa was interested in that line of research, and I just noticed that he had to drop out. But since we're recording this, I'll bring this to his attention afterwards. Thanks. Okay, sure. Okay. We are a little past our time already, but we started late, so hopefully that was okay. At this point, unless there is a burning question. Oh, wait, Roshan does have a question. So Roshan, let me read out your question. In the multilingual separation models, I was curious about how much data would be needed to adapt to a new language and how well these methods would work for phonetically related languages and low resource languages in particular. So he's thinking about the language separation when the languages are phonetically similar.
So for separation, languages don't really play any role in separation. Turns out that the demo I showed where I'm speaking with the Japanese lady, we trained that on Wall Street Journal, on mixtures of Wall Street Journal. So it was American English only, and actually it can separate, like we tried Italian versus German. And it just like, it doesn't care about the actual language content. If it's about the multilingual separation and recognition, then now you actually need to worry about that, yes. And there may be, I don't think we've really studied this, there are errors, like sometimes Italian and Japanese, which can sound similar, sometimes get confused. So there's probably gonna be more errors between phonetically related languages. That being said, we had very little Italian training data, so that's one reason why we had some issues with that. But the about the low resource languages issue, that's using such multilingual systems should help with these low resource languages. Actually, we showed that. I can maybe quickly show the slide. I don't know how to do this. The slide where we had the well, this is going to be a while. The multilingual systems trained on one language versus trained on all languages. and you could see that it helped a lot. Well, there you go. So it helped a lot. The blue versus red is very different, especially in languages where we have little data for that. So Russian, Portuguese, we had very little data. And so training a single system on such small amount of data is very difficult. But if you train a language independent system, their feature extractions layers basically are really able to get advantage from the other languages like Chinese, English, Japanese, where we have a lot of data.
Thank you. I was just,
go ahead.
Yeah, sorry. I was just wondering if there would be a particular advantage to modeling language as well in the separation scenario, not with the ASR. And what you think about whether there would be an advantage to modeling speaker plus language as opposed to just speakers?
It's a good question. I don't think anybody's looked at that. I'm not sure about the language content is really. I mean, the current state of affairs is such that separation. I mean, except in like very noisy scenario, separation is so good that without using any language content that I don't think it matters. But maybe in robust, in very noisy conditions, typically humans, we do rely a lot on our language model to be able to sort of reconstruct what each person is saying. So there could be some advantage of using the language. Actually, we did some experiments somewhat related to this, like Hakan Erdogan in speech enhancement we first separated, then run an ASR system on that, and then we use the output of the ASR system as an input again to the separation, to the enhancement engine. So the enhancement engine knows that it should be looking for something that sounds like these words, and that did help a little bit. So there could be maybe situations where co-training with some separation, with some recognition engine kind of can help in very noisy scenarios.
That makes sense. Thanks for this talk. It was great.
Thank you.
Thanks, Jonathan, again for everything. So guys, we're going to bring this seminar to a close. Just a quick reminder, next week we have Ivan Medannikov from STC Innovations. Remember, these are the guys who pleasantly surprised us all with this very nice, I guess it is a speaker separation technique on the Chime 6 challenge data called Target Speaker VAD. So we'll look forward to his talk. So same time on Friday next week. Jonathan, thanks again.
Yeah, thank you so much for the invitation. Thanks.
All right. All right, guys. See you all next week.
Bye.
See you. Bye.